Yes, we can start.
Okay, Dr. Naveen, please.
Okay, thank you, Dr. Abhishek. So, welcome all the participants on day 4, session 1. And today we are having with us Dr. Mayank Swankar sir from IIT. He's an assistant professor in the Department of Computer Science and Engineering at IIT Varanasi. He earned his BE in Information Technology from Jabalpur Engineering College in 2011, MTech in Wireless Communication and Computing from Indian Institute of Information Technology, Allahabad in 2013, and a PhD from IIT Indore in 2019. His research interest encompasses network and system security, focusing on areas such as network traffic classification, zero-day attack detection, network tunnel identification, VoIP spam detection, and intrusion detection systems. He has authored several research publications in international conferences and journals of repute. He also leads the Threat Intelligence Gathering and Analysis Research Group, which investigates various network security issues, including zero-day attacks and botnet detection. So now we'll hear from Dr. Swankar, sir. Over to you, sir.
All right, thank you. So let me share my screen. So is my screen visible and am I audible?
Yes, sir.
Please either say yes or no. Is my screen visible and am I audible?
Yes, sir.
Okay, thank you. So today I'll be discussing about the use of AI in network traffic classification and especially for IoT devices, how it is being utilized and real-time and real-world technology. So this is the table of content. Then first we talk about basic network security and the motivation to choose IoT network security. Then introduction to network traffic classification and what we have done in this work. And then we will tell you about the results obtained and all such things. So let me, okay. So so network security basically takes the protection of data and network breaches for intrusion detection systems and any other types of threats. And the requirement of security is based on 5 different pillars, which are confidentiality, authentication, integration, or we can say integrity, availability, and access control. And latest area where this is being implemented, and I'm saying that we are using AI a lot in this area. That includes wireless network security, IoT, and M2M communication. That contains mobile-to-mobile communication, software-defined network security, cellular communication security, and many more. And in this area, we'll be working, and we are working, and then we'll see why we are working on security of IoT. So we can see from this figure that we have taken this figure from iotanalytics.com and state of the art, that the number of IoT devices are growing worldwide. And we can see that till 2025, we are expecting to have 34.2 billion IoT devices in the world. And from 2018 onwards, this growth is very high in terms of new IoT devices coming into picture and they are being used. So what are IoT devices? Well, these are the embedded devices connected to the internet. Okay. Usually, not all the time, usually they are power constrained, small wireless connection, and memory constrained. So it may be power constrained, or it may have small wireless connection, or it may be memory constrained, or it may have all those things all together. So in all such cases, there are different types of constraint which result in different kinds of compromise or cyber attacks that is possible on such IoT devices, and can easily compromise and may become a part of a bot, or can have any other kind of attacks, say DOS attacks and DDoS attack and so on. So the research areas for IoT network security is IoT net. The foremost, the most important area is IoT network traffic classification. So suppose in an environment, if you have 100 IoT devices, then in a network, can you identify those 100 IoT devices accordingly, like device 1, device 2, and device N? Why? Because there are many challenges here. These devices are of different vendors, different capabilities, as well as they produce such a heterogeneous network traffic that creates different kinds of network issues. And if one of the network device is being compromised, then how to identify that network device only? And let us allow to pass all other network traffic as normal network traffic. So this is the challenge of network traffic classification. Then application specific IoT attacks detection. That is another part that can be utilized. Like IoT devices use a different application protocols like MQTT is there, COAP is there, HTTPS is there. And there are so many different applications which these IoT devices used. And these protocols are specific to IoTs only. And this is the reason these protocols are widely utilized by attackers to perform different kinds of attacks. And using machine learning traffic to classify these attacks on IoT network traffic classification is one of the important things to be done. So here we present one of our recent work, which is BitIoT. BitIoT is a zero-knowledge bit-level network traffic classifier for MQTT-based IoT devices. So this traffic classifier does not require any knowledge, or does not, so it is not at all supervised. It is totally unsupervised one, which uses ML and also uses statistical method together to perform classification. Okay, the reason is that whenever a network traffic passes, the network traffic is in the speed of 1 Gbps, or you have 100 Mbps of network connection, or 500 Mbps of network connection. So this means millions of network traffic, millions of packets passes every second from a network. And still ML and DL are not fast enough so that they can cater so high speed. They are good for offline work, but for online real-time network information, ML and DL usually don't work in real time. Okay, so this is the reason why we utilized ML with statistical, because statistical is very fast. It can cater the need of this network speed. And then we utilized ML at the background to provide support to these statistical work. Okay, so this is our work, BitIoT, which is a zero-knowledge bit-level network traffic classifier for MQTT-based IoT devices. So let us have an introduction to network traffic classification. So suppose, let me change the color. Yeah. Suppose this is internet and this everything is at your home. There's so many devices like different type of IoT based cameras, different IoT applications like Pixstar photo frame, you have Tribi speaker, HPNV printer, and all are connected to wireless. Even you have energy management systems like light bulbs, power plug, home power plug, bulk-in switches, bulk-in monitor. For controller hubs, you have Amazon Echo, Samsung Smart Thing, and for health monitor, you have different health devices like with link sleep monitor, with link scale, that Metro space station, and so many. So you are having an IoT devices in your home. And before this thing goes to internet and thing comes to the internet, at this point, we need to classify these network devices. The packets, if packet P1 is coming from Samsung Smart Cam and packet P2 is coming from Belkin Motion Sensor, we need to identify. Because sometime if Samsung Smart Cam came under cyber attack or is get affected, then we need to block the traffic of only Samsung. We don't need to block the traffic of all other devices. So we need to identify that device in a network. So we need to identify these packets. If there are packet P1, P2 up to PN packets, then among these PN packets, what packets are generated from which device is utmost important. So this is known as network traffic classification. So it is the mechanism to categorize the embedded devices connected to the internet. It is beneficial to ensuring security, reliability, quality of service, and proper functioning of IoT devices. So this is important. So this is the first step of security. Network traffic classification is the first step of any cybersecurity. So this is about generic network traffic classification. So let's see what work have been happened earlier. So when I said that there are packets, packet needs to be classified. So first they need to be analyzed for classification. For analysis, these packets have like shallow packet inspection and deep packet inspection based methods. All the methods in literature are divided into two categories. So first is for this one, shallow packet inspection. So this paper was published in 2019. This method aims to perform IoT device classification based on feature ranking based framework. So this method utilizes naive-based classifier, different classifiers like random tree, bagging, random forest, SVM, and all together. And then based on whichever perform best, they give the result. Classification tree achieved the highest accuracy of 98.1 on all feature datasets. The limitation is that method is not suitable for obtaining optimal weight for best parameters. Then in 2020, this IoT devices classification is done by one class clustering. So they used k-means clustering and principal component analysis, and they achieved the overall accuracy of 94%. The problem with this paper is cluster overlapping. This means one IoT devices is becoming a part of more than one cluster. This means they cannot result in, we cannot make sure that that IoT device belongs to which cluster, or that packet belongs to which cluster, that the packet belongs to IoT device I1 or IoT device I2. This is not sure because of cluster overlapping. Now, another mark of shallow packet inspection is IoT device classification based on federated learning. So they use FedCNN and FedLSTM method, and they achieve the accuracy of 87 and 88%. And the good thing is that they tested on different applications of this IoT devices. And the limitation is there are loss in models which are based on node failures. Okay. Then in 2022, Wang et al. perform that IoT device classification using multi-scale feature attention approach on bit, byte, and flow stream. Okay, so what they use the CNN model, and they achieve the highest accuracy. So they have performed various experiments, and among all experiments, experiment E1, E2 up to EN, the best result came out to be 98.8%. But remain again the performance issue. Why this is not fast, and uh, they need to be implemented on real-time network traffic, that become a problem. Then comes, so these are the shallow packet based inspection method. There are many methods. I have just catered only 4 best methods which were available, which I have studied, because if I'll go in literature, it will take 2 to 3 years just to cover literature. So then deep packet inspection based methods. Year wise, so Zhu et al. In 2019 made a multi-dimensional behavior profiling of IoT devices on edge network based on byte level information. So what they use the similarity and correlation between different features. Accuracy is, so they pair the IoT devices based on the similarity score. Okay, that if packet P1 is known to belong to IoT device I1, then if P2 is showing high similarity with P1, then we can say P2 also belongs to I. Okay, but again, this lacks the performance because this threshold, whatever they have said, is manual and result in high misclassification. In 2020, app detection is used by Hubbali et al. This is one of my paper as well. I'm also one of the author. To probabilistic bit level signature generation. So we defined this PCDA. This is an automata, probability constrained deterministic automata, that achieve the recall of more than 95% on 40 bits of application. This method is not suitable for encrypted traffic, but for text-based protocol as well as binary protocols. So another paper, this is Khandet et al. Paper in 2021, which uses IoT traffic classification using specific keywords on byte layer. Okay, so this is a DPI based method known as IoT Hunter. It achieved the maximum recall of 99% keywords and utilizes MAC address as well for classification. The limitation of this method is it is computationally expensive, and the issue is that again it is using keywords and thus suitable only for text-based protocols. At 2022, again Hubali et al. Worked on keyword matching based classification, which is again a DPI based classifier, and achieved the accuracy of 98%. Again, the problem is with this method is suitable only for text based protocols. Now, what is the motivation of our work? So issues in IoT device classification due to periodic updates. Why? Because IoT devices are updated by the vendors, which are like once in a month, twice in a month, or 3 times in a month, which changes the signature of the application. So suppose a classifier is made that is trained on IoT device I1, that can classify that IoT device. But after the update, that training doesn't work. So this is the reason these periodic updates is a big problem for classification. But even periodic updates are required. Otherwise, security and the quality of service of this IoT device will degrade. Second, issue of recognizing unknown devices. So if IoT devices I1 to I10, this model is being trained. But what happens if device I11 came into picture? Will classifier able to classify or identify that is it a new device, or it will classify in one of these 10 devices based on high similarity? So this is again an issue. Then time and space complexity issue, because network traffic classification needs to be done very fast and should be near to the real-time classification. So, and variety or limited number of IoT devices for classification. So you have a lot number of devices, like you have heterogeneous environment. Okay, so not only you have IoT devices in that environment, you also have your PC, you have your mobile phones, okay, and so many things in this network which you utilize for different work. Okay, so this makes the network traffic as a mixture of traditional devices as well as IoT devices or smart devices. That is a problem. So what we did, this is our proposed architecture. So the proposed architecture has two phases, training and testing. So in training, what it does, first we take input as network traffic, and network traffic is taken as input. Then we pass this network to make flows, and we perform flow reconstruction. After flow reconstruction, these flows are made. Then we cluster these flows based on different parameters, and all these flows are bit level, or you can say binary one. Okay, then the signatures of each IoT devices is being generated. And after these signatures, so if there are 100 IoT devices, 100 signatures are there. 1000 IoT device, 1000 signatures are there. Then for when classification needs to be done, for matching 1000 signature one by one is very typical. So we made our new data structure known as bin map that keeps the track of all signatures at a time and can classify all IoT devices all together simultaneously. Okay, so this was the training phase of BitIoT. So let's take a look on each module one by one. First module is flow reconstruction module. So whenever a TCP flow is being created, so whenever this SYN, and all happens, so anything between a TCP connection and TCP disconnection is a TCP flow that we made from network traffic at the first step. Then flow is uniquely identified by these five tuples: source IP address, destination IP address, source port number, destination port number, and transport layer protocol. Now at transport layer, you have two different type of protocols, TCP and UDP. Therefore, you have two different type of flows, TCP flow and UDP flow. Okay. Then after these flows are made, then first n bits are extracted from these flows. For example, the flow 1 having bits like 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, and so on. Then we extracted first n bits only for classification and left at that. Okay, so that classification will be very fast using some bits only, as well as also it doesn't hinder the user's privacy. Because if we read everything, the data will also be read completely, and user's privacy will be hindered. So we also keep the user data private, as well as we extracted initial bits for faster classification. Then comes the clustering module. We use hierarchical clustering model. So BitIoT uses F cluster method for clustering each binary field. So F cluster is a standard method of hierarchical machine learning technique, and it clusters each flow based on respective device without using class labels. Okay, so this is how this type of clustering needs to be done on these flows. Once clustering is done, then for each cluster, this is being done. For suppose these flows F1, F2, F3, Fn, all are coming in one of the cluster. Then we generate the signature of that cluster. How we generate it? So any signature will remain, like if for all flows in that cluster, the first value of bit is 0, 0, 0, 0, then the signature is also 0 at first bit. If it is 1, 1, 1, 1 remaining fixed, then that will be 1. Similarly, 0, 1, 1, 0, 1, 0. But for some bit, like here, 1, 1, 1 is there, but this bit is 0. This is not consistent. So here we put star. Similarly, here also 0, 1, 1, 0. So there is a no 1 in all position, no 0 in all position. So here again star. But wherever it is consistent, it is 0 or 1. So this become the signature for that IoT device or that cluster. Okay. So this is how, if there are 100 clusters, 100 signatures will be generated in the same manner. Now, after generating signature, if there are 100 devices, so 100 signature. So matching these 100 signature during testing, one by one, is totally inefficient. It will reduce the speed. So we need a simultaneous matching, that all signatures should be tested at once. So we propose a new data structure known as bin map. Okay, so how this bin map works? So BitIoT generates bin map from each signature generated by the signature generation module. Bin map generation and updation explained through the example. Okay, so let us take an example how this bin map work. Suppose this bin map is an empty two-way graph where you can say 0 on one side and 1 on another side. This is the root. So when the first bit came, which is of signature 1, so from root it will go to 1 for signature 1. Signature 1 is for cluster 1. Then next bit, suppose, so next bit is 0. Then again for signature 1 it is 0. Then next bit is 1, and then next bit is star. So this is signature generation for 101 star. So if this is an empty tree, so how this 101 star, which is for signature S1, enters in this? First 1 comes, which is the first bit, it is entered here. A direction is made for signature 1. And then for 0, it is made here, which is 1, 0. Because from 1 it will go to 0. Then again to 1, from 0 to 1 it will go with signature S1. And then there is star. Star means it can go to any side. So we put the arrow on both the sides for S1 and S1. Now, another application, signature S2 comes into picture, with signature value is 0110. So how it is entered? So it is, first signature is already entered here. Now let us enter the second signature. So 0 comes, so here you will put 0 with signature S2. Then 1 comes, so 1 with signature S2. Then again 1 comes, so signature S2. And then 0. So here what will happen? This will have signature of S1 and S2 both. Because from previous step S1 comes, from the newer step S2 comes. So this is how it is updated with. So if there are 100 signatures, this will be updated for 100 different signatures. So now if we update with another signature S3, with the value of signature as 0 star 1 1. So first 0 is entered. So this was the tree after making signatures of S1 and S2. So let's insert S3. So S3 is inserted. S2 was already available. S3 is now added. Okay. And similar steps. Whatever happened in first two steps, this is how it has been updated. And now this tree has signature for S1, S2, and S3. Okay. So, and now this is for signature S4, whose value is star 10. So if it is star, then both side you need to put signature. Here also star, both side you need to put signature. It is 1, then only from 0 to 1 and 1 to 1 you need to come. Only to 1 you need to come. And from 1 you need to go to 0. So this is the updation after 4 signatures are inserted in this tree. Similarly, you can insert the signatures for different length. Now this is how training happens. So in training, we'll use clustering for ML and use data structure for statistical method, because statistical is much faster than ML and DL. Now, at the testing phase, again, so whenever an unknown network traffic comes, that unknown IoT device or known during testing, then flow classification, flow reconstruction module, network flows are extracted, and these are now matched in the classification module, that whatever tree is created here, this loaded tree with signature is utilized to classify these flows. Okay. And whatever remaining unclassified, they are again passed to training. So this is the proposed method, classification module. So this true module, this flow reconstruction remains same as that of training. So let us see how this classification happens. So suppose this is the already constructed loaded tree. Now a new flow came with 1011 value. Now we need to match that this flow belongs to which IoT device, which signature. Then how it is matched? So first value is 1. So here it is matched with 1. This means this is matched with 1. So what we will do? We increase the counter of signature 1 as 1, signature 4 as 1, because both the signatures are available as this. Okay. So I may increase the size so that it is visible. Yeah. So matching the flow, first bit 1. So what is first bit is 1 this side. Here what signatures are available? S1 and S4. So S1 is made 1, S4 is made 1. S2 and S3 didn't match, so keep the counter at 0. Next is 0. So here we traverse till here, then we traverse from here to here. So what signature is there from here to here? S1 and S4. So again, increase the count of S2 and S4 by +1 and +1 because both the signatures are available. And do not increase the count of S2 and S3 because it is not found on the path. Next comes the signature value 1. So now from here you go to this path, not this path, this path. So this path you go and you found that S1, S3 and S4 were there. So you increase the value of counter for S3 as with +1, S3, S1 is +1, S3 is +1 and S4 is +1. All are incremented by 1. So this value is 3, this value is 1, this value is 3. Now last bit 1. From here this needs to be go to 1 here. So again the counter is incremented. This become 4, 0, 2 and 3. Once all 4 bits are done, matched, then whatever with the highest counter value, this flow belongs to that signature. This means this 1011 flow belongs to signature S1. This means this flow is of IoT device whose signature is S1. We can say IoT device I1. So we have classified the flow that it belongs to IoT device I1. Similarly, we can also see another example. Let's just see only 2 examples, not more than that. So again, the same loaded tree. So let the first bit come 0. So from root, you go to 0. You found 3 signature, S2, S3 and S4. So increase the counter of these 3. Okay, the next bit comes 1. So from 0, you need to go to 1. From 0, you go to 1. And what signatures you found? S2, S3 and S4 again. So you again increase the counter by 1. So that are 2. Next is 1. From this one, you traverse here. So here, you traverse here. What you found? Again, S2, S3, S4. So here, 3, 3, 3. You matched. Okay. And after you go to 0. And when you go to 0, you find this 1, 4, 3, 4. So at final step, what we found that, okay, it is now matching with 2 signature. In that case, what we need to do, either we'll say that this flow, we are not confident that whether it goes to this signature or this signature, or we increase the length of this tree and then perform the classification until it comes into one of the signature. Okay, so this is how this bit IoT matches. Okay, so again for different cases, it is like that. So let us see the complexity of each module. So the complexity of first module is flow reconstruction, which is big O of F into P, number of flows, number of packets in the network trace, F into P. Clustering is big O of M square, which is the standard complexity of hierarchical clustering. Signature generation module is big O of L into J. L is the number of clusters and J is the number of training flows of constant length in each of the cluster. Then bin map generation and updation module, it's big O of log K because it is creating a tree and trees of only two length. It will go only in two direction like this. So log base 2 is the complexity. Then classification is big O of k, which is the length of the signature or length of the flow, which is both equal. Now we have performed experiment to check whether our method is good or not. So we took two data set. First data set we generated in our lab. It has these number of IoT devices. Okay. And we gave the device ID to these devices so that we don't have to write these big names every time. These are the number of packets available in these devices, and these are the number of flows extracted from each of the devices. And this is the size in MB. So total data set is of 1.3 GB, 1.34 GB. Second, data set is publicly available, which contains these devices, and these are the 9 IoT devices available, and these are the number of packets, these are the number of flows, and this is the size in MB. And this is the data set. This is available in this research paper. We have taken the data set from that. And yeah, so these are the total. This is how we divided the data set into training and testing. So we totally have 22 IoT devices, 9 from this and 22 from this. So we have total for first data set. This is how we have divided the data set, that these number of flows will be used in training and these number of flows will be used in testing. Similarly, for second data set, we use this number of flows for training and these number of flows for testing. Now, when we perform experiment, we perform and then we give confusion matrix. Confusion matrix says, if I elongate it, that my device D1 has 16366 flows. And when I matched with the signature of device D1, how many of them are matched? So these are perfectly matched. If device D2's signature, device D2's application flows are matched with the signature of D1, how many are matched? 0. It's good that there are no false matching. So they are not matched. Only the correct one are matched. But for device D2, we have right classification also and false classification as well. So because there is no method which is perfect, okay, so we got two misclassification in overall so many devices. So we put it like that. Also we have like 111 unclassified one, which is not classified with any of the signatures or which is not matched with any of the signatures from the data set. So this was the result. We also tested with dataset 2. Here we found that D9 signature is not good, which result in so many misclassifications. But again, the number is low. We got good recall value. As compared to these thousands of flows, only 17 or 2 or 11 flows are getting misclassified. Okay, and some are remaining unclassified. Overall, the result is good because fewer flows can be neglected, but for a large number of values, the result is good. Then we perform the sensitivity analysis, that how many bits are required so that our classifier gives good result. Like the example we took. So we took in this example, this flow. This flow is of length n is equal to 4. 4 bits are there. Okay. So when we tested with this data set, so these are the result. For 16 bits, result is bad. For 24 bits, result is bad. But as soon as we go with 32 bits, the result improves. Okay. And then we also checked with 40. Okay. So we got similar result with 32 bit and 40 bit. So why to extract 40 bits if we are getting good result with 32 bits? It will be faster than that of 40 bits. Then this was with dataset 1. Okay, so we checked with dataset 1. No, this is with dataset 2. Sorry, my mistake. So this is with recall. So this is the recall variation. So what recall we got? And this is classification time. How much time is required? in seconds to classify all flows of all IoT devices. So we found out that time is very, very near. We increased the bit size, but here we got high accuracy, high precision, high recall at 32 bit. Okay, so 32 was good. Then we checked and we matched our proposed method with state-of-the-art methods. And we first compared with ULFAR. This method uses multi-scale feature attention approach, which uses convolutional neural network, and it takes one packet per flow for classification. And when we tested the same method with ours, we found out that ULFAR somehow perform similarly. And at some step, like here, green one is ULFAR, red one is BitIoT. So here at device D2, ULFAR perform bad, but BitIoT perform good. But at device D3, ULFAR perform better, BitIoT was not. So it happens. It is a normal scenario that not my method is perfect, nor ULFAR is perfect. But what one advantage we got is that our classification time is very less as compared to ULFAR. So we are getting similar, very similar accuracy, but our classification time is faster. So we can say thus, but one of the parameter bit IoT is good or better than ULFAR. Okay, so here, because of space constraint, we have shown only one paper. However, we have compared with 3 to 4 papers. And in each of the paper, we found some advantage over other. Okay, and the conclusion of our work is that we presented BitIoT, which employs bit level signature created from the payload to classify network traffic classification. And for we use F cluster clustering algorithm, which uses first n bits to cluster the flows. Bin map is used to classify the test flows, which is very fast and accurate and perform simultaneous signature matching. We also demonstrated the benefits of our proposed methodology BitIoT by comparing it with deep learning based method ULFAR. And in our future work, what we can do, we can have mixed traffic generated of IoT and non-IoT devices that can be classified this can be a future direction for research, where research can be performed. One of the future direction, there can be more than one future direction. So these are the references. And this paper is published in IEEE Transaction on Network and Service Management. You can find this research paper online. That's it from my side. If anyone has any question, you can ask.